Alright, hello guys. This is Unit 2, Concept A, Essential Knowledge 3, so we're going to be talking about solutions here for a second. Solutions are kind of weird to put in this unit because we're talking about molecules and the interactions. However, solubility is kind of a little important here, as well as interactions between solute versus solvents. So it kind of feels a little bit out of place, but it does fit in, I promise you. I'm going to step aside so you can copy down your notes, and then I'll come back and we'll talk about this. And we got a couple of more notes today, so we'll be writing those down as well. All right, bye. Alrighty, hopefully that was enough time for you. Just basic solutions. There are two main types. There's homogeneous and heterogeneous, or if you are fancy-dancy, it's homogeneous and heterogeneous. But we are not fancy here. We are down to earth, so it's homogeneous and heterogeneous. These are based on the macroscopic view, so just if you look at it with your naked eye, whether or not it looks the same or is uniform, or heterogeneous are not uniform. Generally not uniform solutions have more than one phase present. So I look at the solution and it's chunky. All right, if I look at a solution and there's bits of stuff floating in it, that's heterogeneous or heterogeneous. Homogeneous, it would look the same throughout. There's a couple of other tiny details to help us know if it's a solution or not. Solutions, the solute is the solid dissolved in the liquid. So the solute is the solid, the solvent is the liquid. Usually our solvents are water, so what we do is we take a powder, we dump it in water, we stir it up, and it dissolves. That would be a solution. So in here, the solute or that powder cannot be filtered out. All right, so if it's truly dissolved in there, it will not be able to be filtered out. If it can be filtered out, it's not a solution. It's a heterogeneous mixture, but it's not a solution. Solutions must be homogeneous mixtures. Okay, so the solution must be homogeneous. Heterogeneous are just regular mixtures; they're not solutions. A solution could be a gas or a solid. Technically, you could have a solution of gases, but you don't really usually hear that. Usually solutions are liquids. And the other one is that the solution is clear, meaning that light passes through it. This does not mean the solution is colorless. Colorless is something different entirely. Colorless means that the solution does not have a color. Clear means that the solution does not absorb or deflect light at all. So for example, muddy water would not be clear. Muddy water, the light would be scattered. All right, that would be considered what's called a colloid. But so clear just means that light passes through it. Colorless means that there's no color. So I can have a green clear solution, meaning that it's green and light passes through it. All right, they don't have to be the same thing. They're not the same thing. All right, so that are basic properties of solutions. We do have a couple more notes about solutions, however, because believe it or not, solutions are kind of, pivotal to chemistry. A couple of basic separatory techniques. So separatory techniques. Boy, that does not look like I spelled it right. Let's take a look. Yeah, okay, good. All right. Our first separatory technique we're going to talk about is chromatography. Chromatography. By the way, there are hundreds, thousands, millions of separatory techniques. I could separate a heterogeneous mixture by picking out the chunks. I could separate a heterogeneous mixture by filtering. These are separatory techniques for homogeneous mixtures, and they're a little bit more in depth. Chromatography is a way that I can separate it based off the strength of its intermolecular forces. So we all did chromatography in lab on the year you took honors because you put, let's say, ink on a piece of filter paper and then let water pass through it, and it separated into its different component colors. How far the colors moved was a function of its size and the intermolecular forces between the compounds. Compounds that have very high intermolecular forces tend to clump together and don't move through the paper as well. However, chromatography can also be done through columns, liquid chromatography. It's the same general idea, but instead of running your color through paper, you run it through like a gel solution. And the gel can tease out the different colors even better. By the way, this is how they separate out DNA to do DNA analysis. You run it through an electrophoresis gel. That's a different lecture. Okay, the other one is distillation. Did I spell that right? Yeah, everything looks like I'm spelling it wrong. Distillation. All right, now distillation takes into account the different boiling points. So in distillation, we take a sample and we heat it up. And different parts of that solution will boil at different temperatures. So let's say I have alcohol and water solution. Alcohol will boil at a lower temperature. So as I have that alcohol and water solution in a beaker, and I heat it up, the alcohol will start to come off in steam first. Will start to turn into gaseous alcohol first. And what I can do is very easily just collect that into a tube, cool it down, and have a beaker of just alcohol at the end. And all the water will still be in the beaker because it hasn't reached the water's boiling point, but it's past the alcohol. So as I'm heating it up, the alcohol is coming off as steam or as alcohol vapor. It's being collected somewhere else, and all I'm left with at the beaker in the end is just water. That's how you distill like liquor or moonshine. And when they talk about things being triply distilled or doubly distilled, that's just taking that alcohol and doing the process again to make sure you get rid of all the impurities. Boiling point, we talked about how states of matter are a result of intermolecular forces. So boiling point is essentially the result of intermolecular forces too. The compounds with weaker intermolecular forces will boil off first. So you'll get your methanols to boil off first, then your ethanols, your propanols and your other things. And that's why you can't just make your own moonshine, because the first thing to boil off is methanol, and if you drink too much methanol, you go blind. So that's why they regulate moonshine. They don't just let anyone make moonshine, because there's a little bit of a detail there. So don't distill your own liquor is the message. So parents watching, I just told you, kids, don't make your own liquor. All right. Last but not least, two more things. Let's talk about forming solutions. All right, so when I make a solution, so when I take that powder and I mix it in, it's going to be endo or exothermic. Making a solution is endo or exothermic. Meaning that when I make that solution, it's either going to heat up or cool down. And most of the time, it's so slight you don't even notice it. But if you're making an acidic solution, it will heat up. If you're making a basic solution, it will cool down. But when I just make a regular solution of whatever, you don't really notice it because the temperature change is so slight. And that's because when I make these solutions, I'm affecting the intermolecular forces, and there's energy in those intermolecular forces. So the energy is either released, making the solution hotter when those intermolecular forces are broken, or energy is required to break those intermolecular forces, meaning that the solution will cool down, making it colder. If it's an ionic compound, they are separated and dispersed. Meaning that they don't really break, we don't really affect the intermolecular forces at all. What's happening is if I have NaCl, Na and Cl are held together essentially by a positive and negative charge. When I put that in water, they break apart. The water gets in between and separates and disperses them throughout. That's what dissolving is. Fun factoid for you. It conducts electricity. So ionic solutions will conduct electricity. So pure distilled water will not conduct electricity. So it's perfectly safe to swim in distilled water because lightning won't conduct through distilled water. However, it's impossible to find a distilled water lake because all water that's not treated will have some ions. So when lightning hits water, it's actually being transferred through these electrical charges in the dissolved solutes. So that's why you're not supposed to swim when you are in a lightning storm, because the lightning will hit the water and it'll be conducted through these ions, not necessarily really through the water. But since all water has ions dissolved in it, it's always a bad idea to swim during a thunderstorm, in case you didn't know that. Last but not least, we have one little bit left, and that's on concentration. Okay, that's on concentration. It's great that we just toss in some powder, dissolve it in water, and make a solution. However, it's kind of important to know how concentrated or dilute our solution is. So what we use in chemistry, we measure concentration by we measure the moles of solute. Remember, solute is the powder. Over liters of solvent. And in most cases, solvent is water. We call that molarity. So molarity equals moles of solute over liters of solvent. Or we abbreviate it, molarity is M equals moles per liter. Okay, and that just tells us how concentrated the solutions are. Alrighty, well that's it for our A essential knowledge, or whatever, you know. So that's it for A, so I hope you guys had fun, and we'll be back again starting 2.B. Alright, see you later.